So we're starting here with the Year 12 mechanics course, and the first chapter is on modelling. Now, this is an awkward chapter, and really it's a chapter to be revisited. The first time through, we'll introduce you to a lot of new ideas and new concepts, and really they're ideas that we need in order to do the rest of the mechanics course. So we'll find out all sorts of things, and at first hopefully they'll make a bit of sense. If you're doing physics at A level, then you'll have met a lot of these ideas already, but we need to start somewhere, and we need to introduce a lot of new ideas like the sort of forces we get: friction, tension, compression. We need to introduce these ideas of particles and rods and laminas and things. But until we actually start applying some of the information in Chapter 8, it often doesn't really sink in, it doesn't really make sense. And of course we can't apply it until we get onto the later chapters. But if we jump straight in at Chapter 9 or Chapter 10, then we'd be confused because we haven't got the introduction to some of these ideas from Chapter 8. So if Chapter 8 doesn't make complete sense on your first time through it, I wouldn't panic too much. I would go through the rest of the chapters and then come back to it and see if it makes more sense. Some of it will definitely make more sense, and then you can just look at a few bits and bobs to polish up the rest of it. First idea then. Section 8.1, we're looking at constructing a mathematical model, and I'm going to sort of take a step away from the book for a minute and just talk about the idea of a model in mathematics. Now, what a model is if we have a situation in real life and we're trying to use maths to help us deal with that situation, we aren't going to be able to deal with all of the details and all the fluctuations exactly, so we're going to come up with a simplified mathematical version of it, okay? So let's take an example that we're all familiar with, just a straightforward scatter graph. So we could imagine a scatter graph. This isn't exactly what happens, but let's imagine a scatter graph for the age and weight of children. Okay, so let's say we're going to start at age 5 and go up to age 15, and I'm sure this is an oversimplification, but this is the sort of thing that we might get. We might expect, say, a positive correlation, for example. And what we then do is we draw ourselves a line of best fit, and if we've learned a bit of statistics, we might know that we can find the equations of line of best fit and things like that, but we have a line of best fit. So the real situation is those points all there, all over the scatter graph, all the individual crosses. Any actual person will grow from age 5 up to age 15, and if they, if they're growing in line with what usually happens, most people, they'll be somewhere close to this line of best fit. Obviously, you've got some people are very short, some people are very tall, so some people would be outliers on this graph. But overall, you've got some people. You've got your weight at any age would be close to the line of best fit somewhere. Okay, so if you're worried about a child's weight, you'd go to the graph at, say, age 10, and you'd read up to the line, and then you'd read across, and you'd say, okay, this is the typical weight, and if they're a long way away from that, then we'd treat that situation accordingly, right? Now, the point here is the line of best fit is the mathematical model. We can't take into account all of the possibilities and all of the reasons for being a long way away from the line of best fit, but we can use the line of best fit as a simplified version. So if we say, well, what weight would we expect somebody to be at age 12? We can use the line of best fit, and that will tell us a ballpark figure. And obviously, in the real world, we'd have something a bit more sophisticated than just a single line. I have young children, and when they're born, that you get graphs like this, which sort of this kind of shape, and there's lots of lines like this, which is the age and weight. And you'd expect them to be, the median curve would be here, and then there would be, these are kind of percentile lines. So, for example, maybe if they're below this line, that will be the 10th percentile, and this could be the 90th percentile. So if they're out, if they're on this curve in the middle, they're exactly average. If they're below this curve in the middle, then they're below average. And if they're a long way below average and below, say, the 10th percentile line, then you might start worrying about it. Or if they're above the 90th percentile line, you might start worrying about, so it's a bit, even the models that we use in the real world are a bit more sophisticated. But the same thing is true. The idea is we have looked at the data, we've looked at the real world situation, and we've used that to create a bit of maths that we can follow. We know the equations of these lines, we know the weights we expect children to be, or we know the equation of this line of best fit, we know the weights that we expect children to be, okay? Now, that model is a useful model. It's not going to be exactly true that any child is exactly on this line of best fit, or that any child is, even healthy children might be outside of this range for some reason. Maybe there's a child who's perfectly healthy, but for some reason is low in weight or higher in weight. But it's a useful bit of mathematics that tells us the first piece of information. Is this child a normal weight, normal in the statistical sense of the word, meaning close enough to the average, or not, okay? So once we've got that, once we've got our mathematical model, it's still only going to work for a certain amount of time. So once these children on this the simplified graph here get over age 15, we're not going to expect this graph to carry on. So if I carried this straight line graph on, let's assume it was a straight line graph, and I said, okay, well, over here at age 25, I'd now expect somebody to weigh this much. Well, it's not going to work by age 25, is it? Between 5 and 15, people are still growing, and the main difference in weight is going to be because you're growing. After you get to, we'd expect this line of best fit to actually alter some way, somewhere maybe around 18, when people are reaching their grown-up height, and people stop growing, then you'd expect the graph to change in some way. So two things. Firstly, the model is an oversimplified version of reality, but it's useful in that we can use the maths to predict something. What happens in reality is not going to be exactly what the maths predicts, but it's going to be close enough to be of some use. Secondly, the model works for as long as the model works. We can't say, well, this is always going to be the case. So we can't say over here, when somebody's age 25, we can still use this model that we designed for ages between 5 and 15. So in the mechanics course, we might have a situation where we have a car going along a road, and it's traveling this way. Let me see what can happen. So if a car's traveling this way, we might say that it's got it's got a certain velocity in that direction, and then somebody puts the brakes on, and it then slows the car down. Now that so maybe the brakes are applying a certain braking force, the car's decelerating, and it gets to a full stop, and it stops at this point here, for example. Okay. Now after that, so we could use an equation to model what happens when the car starts braking to when the car stops braking and it reaches a full stop and it's got a velocity of 0 here. Now after that, we're then going to need a different model. What's going to happen to the car after that depends on what the driver does and whether the driver restarts the car or, well, not restarts the car, let's assume they're not stalled, but whether the driver starts driving again, changes gear, starts accelerating off or turns the car around. What's the car going to do? So the model's only going to work for the appropriate circumstances, in this case, until the car's actually stopped. So this is the idea, okay? And that's what they're trying to express in this Venn diagram here. You've got a real-world problem, so we set up a mathematical model. We find a mathematical thing which we can describe. We make the equations easy enough so that we can do the equations. And in doing that, we make certain assumptions. We say, well, we're going to assume that this child is, doesn't have some sort of medical condition that means they're going to be unusually heavy or unusually light, or we're going to say, the assumption is that the car is braking and keeps braking with the same braking force all the way through, that sort of thing. And what is it that's changing? So the age of the child is changing, the weight of the child is changing, or with the car example, the speed is changing because we are applying a braking force, okay? Now, the key bit here is that we make the maths easy enough so that we can do the maths. Obviously, that depends on how much maths we can do. So the more maths you learn, the more sophisticated the model can get, and the closer to reality you can get, okay? So if we collect an awful lot of statistical data and we deal with it with very sophisticated statistical models, then we can make better predictions than if we just have a small amount of data and we make a rough scatter graph and line of best fit sort of model, okay? So you're going to solve, so you take the real world problem, you find a bit of maths that looks a bit like that, you solve the maths using the maths knowledge, then you look at it and you say, okay, how do we interpret this in the real world scenario? So what does this predict, or what does this tell us we'd expect to happen next. If that's a good answer, if that seems sensible, then you can say, okay, well, this is what the prediction that our model is making. So in this situation, we could say, well, this 10-year-old is this weight at the moment. We'd expect them to be this weight this time next year, okay? Or if you get a silly answer, you say, well, okay, why is this model giving us a bad answer, all right? So that's our idea with mathematical modelling. Let's have a look at example 1. So the motion of a basketball as it leaves a player's hand and passes through the net can be modelled using this equation, where h is the height of the basketball above the ground and x is the horizontal distance travelled. So let's see what that looks like. If we look at this from our knowledge of the Pure Maths book, hopefully you can see this is a quadratic, right? The coefficient of the x squared is negative. So what kind of quadratic is it? Well, it's that shaped parabola, isn't it? Okay, so it's it's a that shaped parabola. So and this is actually a parabola is the shape that anything makes. If you throw something through the air, as long as it's not something like a piece of paper where air resistance is going to matter. If I took this pen and threw it through the air, or I don't know, I've just got a pound coin here on my desk. So if I take this pound coin and throw it through the air, it's going to make a parabolic curve through the air. Okay. So if I take it basketball and I throw it through the air, the shape it's going to make is a parabola. And in this case, they're telling us the particular parabola is this. Okay. So h is the height of the basketball and x is the horizontal distance. So if I put that on a set of axes, we've got an x-axis and a y-axis, which is actually now an h-axis, a height axis. Okay. So we can find the height of the basketball when it's released. So when it's released, it's not travelled horizontally at all yet. I've just let go of it. So when I put x equal to 0 in it, I find h, and it's released at a height of 2 meters. So we're going back to our flow diagram here. Is that a reasonable answer? Yes. If I'm throwing a basketball, think about the height of a person. If somebody's holding the basketball above their head and throws it, then that would be, 2 meters tall is a perfectly reasonable height. Or maybe somebody's jumping up, or maybe somebody's, it's basketball, maybe somebody's just very tall. So 2 meters is a perfectly reasonable height for the basketball to be released from. When it's at a horizontal distance of 0.5 meters, so here x is our horizontal distance. So when x equals 0.5, h equals, and we can put that in, and the height it says is 2.5 meters. So when it's travelled 0.5 meters, so when it's 50 centimeters away from the hand of the person that threw this basketball, it's 2.5 meters in the air, roughly. Well, that makes sense. It's gone half a meter horizontally, it's gone half a meter vertically. So again, this model seems to be making some sort of sense here. Now, part B, use the model to predict the height of the basketball when it's a horizontal distance of 15 meters away from the player. So here we go. When we're 15 meters away from the player, we can put in x equals 15, and we come out with h is minus 4. Well, that doesn't make any sense, does it? If height is minus 4, then that means the basketball's had to bury into the ground 4 meters, and that can't happen. So what's happened there is that we've told the maths, okay, let go of the basketball here, it follows this parabola. Now, this is just a function, isn't it? This curve will go on infinitely far in the x direction, infinitely far down in the h direction. So when x equals 15, it's got a negative, sorry, my graph's gone a bit steep, but you get the idea. If h is 15 over here, the curve can go down to 15. But the model, the mathematical model, stops working here. If the basketball goes up, comes back down, and hits the ground, when h equals 0 here, that's the point where our model's going to break down, because the basketball's actually going to bounce off again, isn't it? So we can only describe this part of the basketball's movement using the mathematical model that we've got. And in fact, if you read the question again, this is the basketball as it leaves the player's hand and passes through the net. So really, if this is the player's hand, if it goes up there and down here, if it's going to hit the net, there's your basketball net. It's very unlikely that it's going to hit your basketball net and pass straight through it without bouncing off the net and moving it, altering its course at some point. So probably our mathematical model is only really going to be valid until it hits the net. So we've got to interpret the model using the information that we've got. Now, if you've done the quadratics part of the Pure book carefully enough, you've seen this kind of question before. And on your final A-level exam, you should expect these things to be kind of mixed in. This is half a quadratics question, half a mechanics question, okay? And exercise 8A is just dealing with models in that sort of way. There's not much new mathematical information, but what we are trying to get you to, well, what the example is trying to get you to do here is look through, look at the equations they give you, and look at the words around the equations, look at the sentences, look at the context, and try and get used to thinking in terms of what's happening in the real world, how does that mathematical equation link to what's happening in the real world, and when is the model valid and when is the model not valid, okay? That's the end of section 8.1, or at least as much guidance as I can give you.